This is core component Holy Cross mock, and this is mock 3, and we are up to question 4. And sorry, but the what your teachers suggested might happen is going to happen. You are going to have to draw a graph in an exam. Right, we have got an enzyme reaction, and as soon as you see enzyme reaction, I'm thinking of active sites, activation energy, things like that. State what type of enzyme. Let's have a look what we've got. So with any enzyme reaction, I'm looking for kind of substrate. Reaction is catalyzed by the enzyme, and we've got products. So in any sort of question about with enzymes, that's the sort of thing I'm usually going to need to know. And substrate, hydrolysis of a lipid. So this is a lipid. This is hydrolysis, hydrolysis, so breaking using water, or splitting using water. And the products. Well, I know this one. I know it's going to be glycerol plus fatty acids. And the name of my enzyme. Well, I know that from digestion. And even if I was making up a name, it would have A's on the end. And lipase. So that's the sort of basic information I'm thinking about. So type of enzyme, that's going to be lipase or lipase. What's meant by hydrolysis? So breaking bonds with inserting of water. So breaking bonds using water. So breaking of a bond, and these would be ester bonds, by inserting water. What changes to the pH would have been recorded by the pH meter during the reaction, and why? Well, we're making more acid. So we're making acids from our fats, and so acids, the pH would be reduced. More acidic. Why? Because the lipid has been hydrolyzed to fatty acids. So lipid has been hydrolyzed to fatty acids, and glycerol, but that won't make any difference to the pH. And these have a lower pH. And then we've got an investigation repeated several times, same concentration of enzyme, so that would be our controlled variable, same concentration of enzyme, different concentration of lipid, so different, we are choosing different concentrations, so that would be my independent variable. And then the time taken for the pH meter to record, so time taken, that's going to be my dependent variable. So lipid concentration, dependent variable, and then they've calculated the rate from our dependent variable, but it's still derived from the dependent variable. So we need to draw a graph. When we draw a graph, we're going to draw a graph, and we would have our independent variable on the x-axis, dependent variable on the y-axis. that's going to be lipid concentration and the rate at the side. Here's some paper, and we need to remember our rules for drawing graphs. We need to use at least half of the scale. We need a linear, kind of equally spaced scale that's easy to read and sensible. We need figures at the origin. We need to label our axes, put our units on, plot our points correctly, do a line of best fit, dot to dot with the ruler if appropriate. Those are the things that we're looking to do. 3 marks. It's a lot of work for 3 marks. However, here we go. Let's choose a scale. It's a lot easier if they've put the occasional bold line on, but they haven't, so tough. We need to choose a scale. It needs to go up to 0.8. Always try kind of an obvious scale first. So what happens if we kind of go up in 10 squares equals 0.1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.1. So we're going to get to 0.8. Not sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, there. Is that quarter? Yeah, that's going to be fine. So let's put our scale on there. 0.1, 0.2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.7, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. 0.8. So that just fits on there, and this would be 0. Up the side, we're going to 5.8. So again, if we used a 10 scale going up 1, so that would fit on there. It looks like it's nearly a square as this. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's have that as our 1.0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2.0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3.0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4.0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5.0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6.0. So that's our scale sorted out. And do we cover at least half? Yes. Let's put our axis labels on so we don't forget. This is our lipid concentration. Lipid concentration, and that is in percent. On the side here, I'm just going to copy these down exactly as they are, then I can't get them wrong. Rate of reaction in arbitrary units. They use arbitrary units because the actual units for rates are quite often very small numbers, and they have to times them by 1,000, and then it's per second, or it gets very complicated, and they don't want you to get bogged down in that. They want you to draw a graph and look at the biology. So that's why they quite often use arbitrary units. So let's plot some points. 0.1 is 0.6. So 1, 2, 3, 4, 5, 6. Can you see now, because I've used a sensible scale, it's quite easy to plot. 0.2 is 1.3. So there's 1, 2, 3. You should draw this in pencil. You should draw this in pencil, not in pen. If you draw in pencil, then if you make a mistake like I just did there, then you can just rub it out. And you will make mistakes drawing graphs. 0.3 is 1.9, so there's a 0.3 line, and it goes nearly up to the 2. There we go. 0.4 is 3.0, so 0.4, 3.0. 0.5 is 4.0, so 0.5 is 4.0. You might put your ruler on to help you with this. 0.6 is 4.8, so there's my 0.6 line, so we're looking for 4.8. And 0.7 is 5.8. Yeah, that's easier. It's 5.8. So there's 6. That'll be 5.8. And 0.8 is also 5.8. There we go. And as I'm a biologist, I'm just going to join these up dot to dot. It's much more fun than drawing a best fit. There we are. So generally in biology, unless they instruct you to do otherwise, just draw dot to dot with a ruler and you'll get the marks. So why wouldn't you? Try to get them exactly right from the center of point to the center of the next one. There we go. So that is a hell of a lot of work for 3 marks. The way that they mark these, for this one they're saying, right, you can have 3 marks, but let's take them off for various offences. Incorrect plot, so you've plotted your x's wrong. Poorly drawn curve. Poorly drawn curve. Allow ruled lines. Lovely. Inappropriate scales. For example, if you'd gone up in 0.1s, then changed it to 0.2s, and or made it so it's almost impossible to plot right, or didn't use half the allotted paper. And then have we got our axes with labels on. And you'll note here we haven't drawn down to 0 because we haven't got any data for 0. So we can't just make it up. And what happens to the rate of reaction when the lipid concentration rises from 0.7% to 0.8? So we are looking at this area here on the graph. And go what happens and explain. So the rate remains constant or doesn't increase any further. So the rate remains constant. It doesn't go down. It just stops increasing any further. Why? Well, this is your typical increasing a substrate concentration type of graph. So the substrate or the lipid is occupying all of the active sites. So at lower concentrations there's still spare active sites. whereas here at the top active sites are all occupied. So at lower concentrations, not all active sites are occupied or in use. At 0.7%, all active sites are occupied. The extra lipid or substrate, up to 0.8, can't access these active sites. Can't access the active sites. So you might have said that in slightly different way. You might have said that the enzyme is now becoming limited, a limiting factor. Things that you can't say, active sites are used up or things like that. So 2 marks there, and hopefully you got one of them for just the description. The investigation was performed at 25 degrees C, a controlled variable. Draw a second line on the graph to show the expected results if the experiment carried out at 35 degrees C. Label your line. Right. So, faster at a higher temperature, more kinetic energy, that's what we're thinking. So, it would start off and then go up faster, but this lipid concentration, you've got to think that you still don't want to, get the rate too high. So steeper curve. So something like that. Label your line 35 degrees. So something along the lines of that. And you need to think of, so for each concentration be faster. So our rate actually would go up like that. So label our line 35 degrees C. We are ignoring the effect of denaturing, possibly. It's not much of an increase, but we don't particularly know what's going on. But essentially, a steeper curve, certainly at these lower concentrations. And that's 11 marks, including drawing a graph.